Here in this video, we are solving a very small problem. The problem is like this. There are two soap bubbles, each of radius R1 and R2, and they are kept in vacuum at a constant temperature. What's the ratios of the masses of the air inside them is kind of a question. So let's try to understand what is given to us in the problem. What is given to us? There is soap bubble 1, soap bubble 2. They are spherical in shape. They are having a radii R1 and R2. That means their sizes are different. As their radius are different, the volume of the gas, volume of the air inside is automatically different. As the volumes are different, though the densities are same, their masses inside the air is also different. They are given that the temperature is constant. That means if this temperature is T, this temperature is also T. We need to find the ratios of the masses inside the air. So if we have to find out the ratios of the masses of the air, being this is air, we can assume it like an ideal gas, and we can think of equation of an ideal gas. We know the equation of an ideal gas is PV equal to nRT, where P is the pressure. Each of these bubbles are going to have a different pressure. Why they are going to have a different pressure? Because of the surface tension. They are going to create some excess pressure inside the soap bubble. As that the radius is different, the excess pressure depends on the radius. The pressure inside a soap bubble, excess pressure inside a soap bubble has a formula 4 into surface tension by R. I have derived this equation just in the previous video. If you don't know that, please look back to the previous video of the playlist of this chapter, where S is the surface tension, R is the radius. Because the radius for each of this drop is different, the pressure is going to be different. Volume is different. Universal gas constant is constant for the given gas or for all the gases in the air. Temperature is also given as constant. So I can rewrite this ideal gas equation as PV equal to N, number of the moles can be written like mass by molecular weight and R. Because we want masses, I am writing the equation in terms of masses. So what are the constant in the given problem now? Universal gas constant is constant over the entire universe. Temperature is constant given in the problem. Molecular weight is constant because the same air is present in both the bubbles. So the other terms are variables. What are the variables? Pressure, volume, mass. So with the remaining variables, we can write an equation. What is that equation? Pressure and volume is directly proportional to mass. So writing the proportionalities, P1 V1 by P2 V2 equal to M1 by M2. So that's what we have to find out, ratios of the masses. If we have to find the ratios of the masses, we shall write that as ratios of pressures and volumes. So we shall write an equation for what is the ratio of these pressures and what's the ratio of these volumes. As I told you, excess pressure inside the soap bubble is due to the surface tension, and we can write that equation as P1 as this is the equation 4 into surface tension by respect to radius R1. And for the second bubble, I can write excess pressure in the second bubble is same surface tension because the same air, but the radius is different, R2. So I got already P1 and P2. Volume, because these drops are spherical in shape, we can write the formula for the volume as V1 is 4 by 3 pi R1 cube. That's the radius of the first one. And V2 can be written as 4 by 3 pi R2 cube. Now I know everything. I can just move on and substitute in the formula. Yes, let's do that. It implies ratios of the masses of the air inside the soap bubbles is P1 and P2. We have derived that equation 4s by R1 by 4s by R2 and V1 by V2, that is 4 by 3 pi R1 cube by 4 by 3 pi R2 cube. So what can be cancelled? This 4s and 4s are same, that can be cancelled. This 4 by 3 pi and this 4 by 3 pi is also same, that can be cancelled. So when you simplify that, I'll get the ratios of the masses as this is in denominator of denominator goes to the numerator. This is in denominator R1 cube by R2 cube, the remaining terms. So when R1 gets cancelled here and square remains, when R2 gets cancelled and here also square remains. So the ratios of the masses is ratios of the radius square. That's how we need to solve this problem. That's it. Right. So the ratios of the masses in the bubbles when the temperature is same is directly proportional to the square of the radius. Right. Thank you for watching.